This video describes how I designed and implemented a score server for my game. I make a train game where you optimize solutions to levels to get as efficient of a solution as possible. You try to minimize the score on a level where the score is the sum of infrastructure costs and time. Improving scores is more fun if you can compare against other people's scores than try to beat them. This means that I need to write a score server that keeps track of the per level leaderboards. I go into a fair bit of detail about design goals, implementation, and scaling analysis of my server. This isn't really a tutorial in that I don't go into details of the actual socket API that can be found in documentation. I also don't necessarily recommend that you do exactly what I did, but rather this is a case study of how I approach the problem, and what I did as someone who is more of a graphics programmer than a network expert. Also, I'm not hardcore optimizing the server code. Rather, my scaling analysis is napkin math and illustrates how to approximate performance limits and bottlenecks. If that sounds interesting, then this video is for you. Before designing anything, it's good to understand the goals. I don't expect massive numbers of players, perhaps a max of a few thousand concurrent players. This allows me to favor simplicity over performance. Although my target is low, I'll analyze what limitations I expect to run into with my simple solution and consider how I could scale up if needed. The server should be cheap to run. I want to spend minimal money on server maintenance, especially considering that I'm releasing my game for free, so every cent I spend is pure loss. The server should be minimalistic and efficient. This sort of ties in with cheapness because hardware costs money, but beyond that, my design philosophy in general is that it makes me feel good to rely on as little external stuff as possible and to have a simple and understandable system with good performance. I want to be able to verify that scores are valid. This means I need players to submit their map with their score, and the server needs a way to run the game to check that the score matches what was claimed by the client. I'm hoping that my players will be relatively chill, and I don't have to overly worry about vectors of attack. After all, this is a peaceful game about trains. The server needs to run on both Linux and Windows. Windows, because that's my main development platform, and I'll do most of my testing there. Linux, because servers run Linux, and especially if I need to host a server in the cloud, Amazon EC2 is double the price to run on a Windows server compared to Linux. Since I want to host my server cheaply, a big question is if I need to rent a server from Amazon or if I can locally host the server. There are a couple of benefits to renting. One is reliability. The computer in a data center will have 100% uptime, no power outages, and an infallible internet connection. Using a residential ISP can randomly reassign your IP address. Another is connection quality. Data centers are centrally located to reduce ping and have massive duplex bandwidth, whereas home connections are usually very limited in upload bandwidth. Finally, privacy of having a server with a different IP than your home is nice. And if there are a lot of players, is probably critical. But the cost is cost. Renting a server is fairly cheap if you only need the bare minimum of compute, but is really expensive if you need a lot of computational power. The price of a T4G Nano instance running on ARM is $3 per month, plus a fixed cost of $4 per month for a public IP address. However, if you need lots of compute, a T3 2 extra large instance running on 8 Intel virtual cores is $240 per month. To keep the cost down, I'll start by hosting the server locally. As it happens, I got a decommissioned workstation with first-gen Threadripper for free from a company my wife used to work at. They wiped all the data from the drive and swapped the GPU with the cheapest thing that they could find that generated a display signal, but the computer is perfectly fine otherwise. This has been sitting around collecting dust for a few years, but has 24 virtual cores, 64 gigabytes of RAM, and 1 terabyte of disk space, so it provides the equivalent of about $800 of cloud compute. So I slapped on a copy of Linux, and this will be my server. For simplicity, I'm running the score server on the same machine that the verification happens on, so that I can launch a game process from within the server itself. Although running the server on a local machine could become a problem, it's hard for me to predict if it actually will. I think it's unlikely that anyone will try to DDoS me, but if it becomes a problem, I can re-architect the server to have only the lightweight part in the cloud and have verification run on beefier machines that connect as trusted clients. As a small configuration note, it's necessary to set up a firewall. The server machine itself has a firewall, and I also need to configure my router to forward specific ports to the server machine. Because my ISP assigns IPs dynamically, my IP may change, and I'll need to update the DNS to match whenever that happens. I could also lose power and need to manually reboot the computer. To detect these sorts of outages, I set up a free alarm service by Uptime Robot that will periodically check the status of the server and email me if the server isn't working. Let's consider how many users I can realistically handle based on this setup, given a fairly simple implementation of the server. One of my assumptions is that there won't be all that many players, so let's see what fundamental limitations might exist based on the hardware configuration. For the server to be responsive, I would like it to be able to check each socket around 10 times per second. Another way of saying that is that I have a target latency of no more than 100 milliseconds. The simplest way to check for incoming data is to pull connected sockets one by one using a single thread. This is done by setting the socket to non-blocking using function control when it connects. Calling receive on the socket will return immediately and report if any data was read or not. Let's be a bit pessimistic and say that calling receive results in a system call with a kernel transition that takes 5 microseconds. That would mean that I can handle 20,000 concurrent players responsively, which is already sufficient to handle the load of all but the most popular games on the charts. If that were somehow to become the limiting factor, and it won't, there are more efficient methods to check the status of sockets. The downside of the more efficient methods is that they become operating system specific, which makes it impossible to use the same code between systems, and they add some code complexity. This is a pain for debugging because my main development computer runs Windows and my server runs Linux. In Linux, there's epoll, which allows you to pull large numbers of sockets in a batch. Alternatively, there seems to be a more efficient asynchronous Linux system called IO Uring that I don't know much about. Windows has an efficient asynchronous event notification system called IO completion ports. Any of those methods can handle hundreds of thousands to millions of concurrent connections, which would put me in the top 10 played games on Steam. For verification, I'll only check the score if it's better than the previous best score for that player. Let's do some napkin math and say a player improves their score once every 5 minutes. If it takes 5 seconds to verify a score on a single virtual CPU, of which I have 24, then 24 cores times 5 minutes times 60 seconds per minute divided by 5 seconds to verify gives 1,440. So I can handle 1,440 concurrent players before verification starts to lag behind. It's nice that verification looks like it's more likely to be the sticking point than the server itself, because verification is more tolerant to overloading. First of all, verification isn't even required if I were willing to trust reported scores. So it's fine if verification becomes delayed as long as it can eventually catch up. For example, if fewer players are playing at night, then it may be able to clear the backlog of unverified scores. By delaying, you can also skip verifying some scores. For example, if a player makes several improvements in quick succession, only the final best version needs to be verified. This will be a common case because people will naturally iterate on the same map. People are also most likely to cheat to get low scores. So if the verification tasks become so overloaded that I can't verify anything, or everything, I can triage by preferentially verifying the lowest scores in the leaderboard. In the worst case, verification is one of the easier things to split among multiple computers, and I could either spend money on more computers or find some volunteers to donate compute resources. In short, the server should be more than adequate to handle my expected number of players, and there are reasonable ways to improve scaling or mitigate scaling problems. One of the simplifications I'm making to the server is that I don't have player accounts. For the purposes of a leaderboard, I don't think an account adds much value to a player and adds friction to starting playing. Not having accounts also means that I don't need to store or ask for passwords, and don't have to make a separate login step. I don't need to send email verifications for account creation or have password resetting for lost passwords. Since you can theoretically choose the same name as someone else, I prevent name collisions by also generating a hidden unique ID for a player when their name is chosen. This prevents people from being able to overwrite other people's scores. Now that we've discussed the high level and sysadmin stuff, let's talk about how the server is actually implemented. All communications between the server and client are constructed as logical packets, and the data is generally transmitted in binary format rather than as text. I find that parsing binary messages is far simpler to write code for, is more computationally efficient, and, due to its simplicity, is less likely to be buggy or create security holes. Every packet starts with a header indicating the payload size is a 32-bit integer. This allows the receiver to know when the packet has been fully received, and parsing of the content is only performed on completed packets. After that, I have a byte indicating the message type, and the remaining payload data are the message contents. I'll give an overview of the message types I use, then go into some more detail about the server architecture. The interface of constants for message names is in a shared header between server and client. An important thing to note is that there's a symmetry that every message has a response. Really, I could have a single enum, but I find it's clear to differentiate the messages to show who is making the request versus responding. Something that is extremely important to make sure is that there's always a pairing of send and receive calls. Never send twice in a row, or else you might have to wait 200 milliseconds for a timeout until the second send happens. At least this is what happens for some versions of Windows. Upon connecting to the server, the first thing the client does is send its game version while requesting the server version. From the server's perspective, it will always respond with its own version number, but if the client's version is different from the server's, it will immediately close the connection afterwards. Likewise, if the client gets a response with a different version than it expected, the client will close the connection and set a flag to disable future attempts to connect to the server in that game session. It will also pop up a dialog box informing the player that they need to update the game. When adding a score, the player sends the map name, username, secret user ID, score, and game version, followed by the save file for the level. As usual, if anything is wrong, the connection is closed immediately. Since multiple threads share scores, a mutex is acquired in order to update the score list. The score of that user and ID is immediately updated to the claimed score if the score is better than what was already in the leaderboard. However, the score is marked as unverified. Also, the score list is sorted to make other operations faster. It's preferable to spend extra time when updating scores compared to reading them, because updates will be less frequent than queries. Unverified scores will eventually be tested by running the game to check if the score is reproducible or not. If verification fails, the score is removed from the leaderboard, but I'll go into more detail about the verification process later. The slightly trickier aspect I encountered has to do with how the client deals with server acknowledgments of adding scores. I want to only have the client send an updated score if that score is better than the previous score they had. However, I can't count on the client having been connected to the server when the last best score was achieved. The server could have been down for a variety of reasons. Maybe it crashed or was down for maintenance or whatever. I also don't want to simply track if the score was sent, because sending the score doesn't necessarily mean that the server received or acted upon that message. This means that I need to keep track in the client if the scores have been acknowledged by the server or not. If the score wasn't acknowledged the last time the score was updated, then I should allow the player to send the score again to properly update their standing. Whenever the client wants to display scores for a level, it will request a fresh score list for that level. The request is pretty simple, just sending a string with the level name. The interesting part is the response. Again, since the scores are shared between threads, this whole operation is protected by a mutex. I don't want to send back every score, since that could get slow if there are thousands of scores. Instead, I send back a fixed size response with the top 5 best scores and a histogram of the entire population of scores. These top 5 scores also have their verification status returned, which is indicated by a question mark for the player. I chose to do this so that the player can immediately see updated statuses instead of having to wait for verification. It also allows the score server to function even if there is a problem with verification becoming backlogged or otherwise breaking. The scores are kept in sorted order, which makes generating a histogram fairly fast. The min and max of the range can be found from the first and last entries in the score list, well, conceptually at least. There is a slight complication that I potentially have some scores from an older game version that I might need to skip over, but that's an uncommon edge case. Once the range is determined, collecting the scores into histogram bins then requires one linear pass through the score array. There's no pointer in direction, and entries are reasonably small at 40 bytes, so scanning a few thousand entries is extremely fast, on the order of a microsecond or two. The last message type is that the server will send a heartbeat message to every connected client it hasn't heard from in the last 20 seconds. I added this because I noticed that I was sometimes having dangling connections that were not closing. This is a bit strange to me because I was under the impression that the TCP protocol would automatically handle timeouts and report a connection as closed, which should be indicated by a read of 0 bytes. What seemed to be happening in practice is that the client I'm running on Windows would time out and close the connection, but the server would happily wait forever on that closed connection. I could also get dangling connections by crashing a client, or equivalently by terminating the debug session. So I need the server to periodically send something to test if the connection still exists. If I don't get an acknowledgement within 3 seconds, I close the connection. I'm not entirely sure what a good timeout value is, but some internet searching showed that people have often found that there's a timeout of 21 seconds before a connection closes. So I set 1 second less than that. Frankly, this is just some random operating system setting, so I may have to adjust the timeout to be lower if people experience problems, but it seemed to fix things for me. Great. So now let's talk about the architecture. In terms of the interfaces for network connections, I have 2 classes, Server TCP and Socket TCP. Server TCP is a wrapper for a listen socket. In TCP, the way a server works is that a server will bind a socket to a port to listen for incoming connections. For example, in HTTP, it would bind to port 80. When a client connects to that port, the server will create a new socket to accept that connection. All communication with the client happens through that newly spawned socket via send and receive function calls that look exactly like the calls performed by the client. Thus, both the server and client use my socket TCP wrapper around the socket to send messages back and forth. If I had to describe a theme for my server, it would be queues. Queues of incoming connections, queues of incoming and outgoing packets. Each packet itself is a queue of values, and there's a queue of verification tasks. I'll go into a little more detail. The first queue is in server TCP, where I store a queue of incoming connections. When the server accepts a connection, it creates a socket TCP and stores a pointer to that in a queue. Let me prepare you that I use terms like list and queue in a sense of intended purpose rather than as a name for specific data structures. The queue in this case is actually a standard vector, but the purpose is to buffer connections. Anyhow, the point is that this queue is used to hand off control of sockets from the server wrapper to the outside code that will actually communicate through those connections. The next queue of interest is within the socket TCP wrapper. Each socket has a queue of incoming and outgoing packets. Honestly, the concept is fairly clear, so I'm not sure there's a lot to say about this. A complication of processing packets is that TCP doesn't have a concept of packets, and instead has streams of data. Although the underlying network fabric operates on packets, there is no way to predict the fabric packet sizes, and the logical packets of my wrapper may be split into many network packets. In the extreme, my logical packet max payload is up to 4 gigabytes, which would certainly be split, considering that the IP header only allows up to 64 kilobytes, and the IP packet itself is a logical packet that is larger than the typical max transfer unit of an Ethernet frame, which is 1,500 bytes. In practice, when the client sends score updates, the save file for the level is included as part of the packet message, which could easily exceed any of those limits. Also, there's no guarantee that logical versus network packet boundaries will align because TCP is allowed to combine multiple small sends into larger chunks of data to improve throughput. This means that the incoming data streams need to be stored into an intermediate buffer and split into logical packets based on the packet size header. Actually, I use two intermediate buffers. First is transient data from a given receive call, which is consumed by the packet chunker. The packet chunker data persists between receive calls and consumes up to a packet worth of input at a time, iteratively, until all of the received data is consumed. Whenever a complete packet is consumed, it's put into the incoming packet queue. The packet chunker is slightly complicated because it has to have a persistent state that's updated with the data stream of arbitrary length. It needs to first read up to the size of the payload header, which is 4 bytes, but no more, to determine how much of the remaining data to read from the stream. There is also a potential attack vector that needs to be guarded against, where a huge payload of 4 gigabytes could cause me to allocate that much space per connection and cause me to run out of memory. So precautions need to be taken to check for large packets early and disconnect badly behaving clients. Going the other way of transforming packets to streams is simpler because although the send call may not consume all of the data I try to send in a given call, it will only consume up to as much data as I present it. What this means is that the logical packet boundaries can always align with send buffer boundaries. As I mentioned, the TCP layer is free to merge data from send calls, but I don't need to. So there is still some state handling, but it's minimal. Although I may be able to avoid some data copying by sending straight out of the packet struct, I found it easier to place data that I'm sending into a separate buffer. The complication is that I need to send the size header in addition to the payload. As I mentioned way earlier, performing more than one send per receive call triggered pessimal behavior of 200 millisecond latency due to the Nagel algorithm, which is not actually disabled if you set TCP no delay on some operating systems. This means that the easy solution of sending a 4-byte header, then sending the payload, is not allowed. Somehow the data has to all be contiguous in memory to perform a single send. This could be done, but would be sort of a pain and would disallow using typical containers that have a size, capacity, and pointer to data. Instead, you would need some super custom container that just has a pointer to data, then has the capacity, size, and data all in the same heap allocation if you're going to send directly out the packet struct. Packets are a queue of values that are read or written. These have nice semantic meanings like an integer or a string. To read or write those values, I have little templated wrapper functions to make accessing the data simpler. The packet also keeps track of the state of how much has been read or written. For writing packets, the code is relatively simple because the program trusts itself. So writing a value simply consists of pushing back bytes onto an array. More care has to be taken when reading data from a client, because clients cannot be trusted. This means I need to do extra checks, especially when reading arrays of values that I'm not reading past the end of the packet's array of data, which could cause the server to crash. If such a malformed packet is detected, the packet sets an error flag, and if an error was detected, I will forcefully close the connection. The other reason that packets are interesting is that I separate the concept of an incoming and outgoing packet, and treat reading and writing differently. The alternative would be to treat the operation more generically and have a serialized function that can either read or write using the same code. I've always done explicit reads and writes, and for netcode I don't see a strong argument for a generic solution, because the server and client are often going to be entirely separate programs, and trying to share code can feel awkward sometimes. The case for attempting to share code makes more sense within the same program for reading and writing files. But my experience with C++ has been that this still winds up with duplicate code for reading versus writing, but with an abstraction layer that makes things more confusing. That said, this may stem from a limitation of C++ lacking useful reflection or type introspection, so this observation may not apply to other languages. Lastly, there is also a queue for verification of scores. This was exciting because it's the first thing to directly deal with threads. If you like threads, check out my video entitled Parallel for Primitives, where I go into detail on how to write extremely low latency parallel code. This is largely irrelevant to my high latency server, but I digress. The idea is that there is a queue of scores to verify. I also have a pool of threads equal to the number of processors that will periodically check the queue for if there's any work to do. Access to the verification queue is controlled through a verification mutex. After a verification thread retrieves a score from the queue, I'll launch a copy of the game. The game will return the score, and if there are any errors, and based on those results, the verification thread will update the scoreboard, which has to get access through a score mutex. If the verification succeeded, it will update the score as verified. Note that it can't blindly overwrite the score because another thread may have updated with an even better score in the meantime, so it has to check if the score is better than what's on record. If the verification failed, the score is removed from the leaderboard. It's also possible that the server will have shut down or crashed, and when starting again, there are unverified scores. Thus, when the server is initializing, any scores saved on disk that weren't verified yet are added to the verification queue. There's also another special case where I have updated the game version and there are saved scores from a previous game version. When updating the game version, I may have changed mechanics that made previously acceptable solutions invalid, or I may have made changes to either the simulation or scoring that change the values of scores. In that case, I need to run a special type of update for the verification that can either invalidate the score or update the score to match what the new game version produces. This type of verification only happens during startup and is also added to the verification queue. It's also worth mentioning that the verification is run in a separate process from the server process. This is important for the server stability and security. Because of process isolation, a crash in the game verification code won't cause the whole server to crash. Unlike the server, the game code is something that attackers have direct access to, and can more easily search for exploitable bugs, and so the saved games that players send to the server are more dangerous attack vectors. If I were to be more paranoid, or have a larger number of players to where I'm more likely to be attacked, I could increase isolation by running the verification processes from a separate, more locked down user account, or by running verification on a separate machine. Whenever scores are modified, a global flag is set to true. Once per loop in the main server thread, that flag is checked. If true, the current states of the scores are written to disk and the flag is cleared. This means that the up-to-date state of the leaderboard should be preserved on disk even if the server crashes. The file format is extremely simple. Each line is a score entry with spaces separating the values. Writing an entry is literally a single fprintf function call. I save results to disk in a text format because it's easy to inspect and edit. I expect that the cost of writing to disk should be minimal and on the order of a few milliseconds at most. If the server becomes laggy, either from writing to disk or from any other aspect, writing the file only happens once per loop. This means that the net messages will accumulate and be processed in batch to compensate. So saving the result to disk should never become a rate limiter. If the speed becomes problematic, I could switch to a binary format to reduce cost. The way I store scores in memory is equally simple. As I had mentioned earlier when I described adding new scores and sending score lists, the scores are stored per level as a sorted array in memory. Specifically, The per level score list can change size, so I have them in a standard vector per map. The base struct takes 40 bytes, and there are a couple of strings that contain pointers to player name and save file name, which take an additional 100 bytes or so. However, sorting, moving, or scanning through scores will generally only touch the 40-byte struct. A Threadripper 1920X has 85 gigabytes per second of bandwidth, which means reading an entry takes about 0.47 nanoseconds to read, assuming the data gets prefetched and bandwidth is maximized, which it should be when linearly scanning through an array. That's really fast, so the instruction count is more likely to be the limiting factor. Each loop is tiny and has extremely predictable branches. I don't want to get too deep into the weeds here, but for napkin math purposes, taking 4 instructions per iteration is plausible. With a 4 GHz processor, we can say that reading one entry takes about 1 nanosecond. My target latency is 100 milliseconds, so the target time in nanoseconds is 100 million nanoseconds. Not everyone who owns the game will be connected, so let's assume there are 10 times more scores than connected players. Also, players will not request a score every tenth of a second. If a score is requested every 5 minutes on average, 300 seconds, the probability of requests in any given tenth of a second is 1 in 3,000. Plugging in those numbers, 100 million nanoseconds equals the number of connections times 10 connections times 1 over 3,000 times 1 nanosecond. This is a simple quadratic equation, and solving for number of connections predicts that storing the scores in an array like this can support up to about 170,000 concurrent connections. In practice, I won't have anywhere near my max supported player count, so I want threads to go to sleep when they aren't needed, so I'm not burning CPU power. Again, I use a very simple solution where both the main server thread and verification threads pull queues for work to do. They run an infinite loop where each iteration they check for work to do. If there's work, they do it. Otherwise, they sleep for 100 milliseconds. In an unloaded system, this means that when a packet comes in, it may be at any time within the sleep period. Thus, the response latency is between 0 and 100 milliseconds, with the average being 50 milliseconds. The work will take almost no time, and when the queue is completed, the queue is pulled again, no work will be found, and the thread will sleep. It's interesting to consider what happens as load increases. Let's call the ratio of current load to max load R. This is defined as how long it takes to complete work divided by the time the packets are accumulated over. Thus, while the thread sleeps for 100 milliseconds, packets that accumulate will take R times 100 milliseconds to complete. When the work is done, the queue will be pulled again. But this time, the queue won't be empty. It will have accumulated packets over a period of R times 100 milliseconds while the thread was working, which will take an additional R times 100 milliseconds to complete. More packets accumulate during that time, etc. This forms an infinite series that the time between sleeps will be 100 milliseconds times the sum over I from 1 to infinity of R to the I, which is equal to R over 1 minus R. At 50% load, 0.5 divided by 1 minus 0.5 is equal to 1. So the thread will alternate between working for 100 milliseconds then sleeping for 100 milliseconds. As the load approaches 100%, the time between sleeps will get larger and approach infinity. So what's the max latency of the system? Since R is less than 1, the largest period over which packets can accumulate is during the sleep itself. The packets are processed in order, so packets that come in early are processed early, and late packets are processed later. So the latency is slightly less than 100 milliseconds for any packet that arrived during a sleep. However, in a heavily loaded system, a higher fraction of the time is spent in the tail periods that are shorter than the sleep. Those packets will also be processed in slightly less than the length of the period that they were collected over. So we'll have less than 100 millisecond latency down to almost zero latency for the very tail of short periods. Counterintuitively, this means that latency basically doesn't change even up to 100% load. However, there's a tipping point. As soon as the system becomes overloaded, where R is greater than 1, then the work period of 100 milliseconds times R to the I diverges to infinity, and latency goes to infinity. Although it's great to have the server running, sometimes I need to make it stop running. For example, if I want to update the executable with new code, but I don't want to just kill the process because there's a chance that it'll be in the middle of writing a score to disk. And killing the process would result in losing score data. I assume they'll either have physical access or can SSH into the server machine. The simplest way I thought of to signal a server to shut down is by signals. Specifically, I register a callback function for the sigint and sigterm signals that set a global variable grunning to false. The server threads are running an infinite loop that checks that variable each iteration. When false, worker threads terminate, and the main thread waits for workers to terminate, cleans up, saves the scores to disk, then quits. As I mentioned earlier, my main development environment is Windows. So I got everything working there first, then ported the code over to Linux. I low-key hate build systems, and Linux developers seem to love making overly complicated build systems with domain-specific languages, where meta build system generates inputs to a variety of other build systems that are also overly complicated, have their own domain-specific languages. I don't use any of that junk and just have a simple shell script that invokes the compiler. Anyhow, getting the server to compile wasn't too hard. As usual in porting efforts, it feels a bit Sisyphean in that the error list only seems to grow, because when you fix one error, it simply lets the compiler get farther along to find more errors. There are also random differences between the standard library of operating systems. They're mildly aggravating and feel like they're intentionally done to make porting harder. For example, Microsoft deprecated standard functions like fopen to safe alternatives like fopen_s. They're almost identical. So I needed to make some wrapper functions. Even more aggravating is that I store scores as 64-bit integers, but it took me a long time to figure out how to print a 64-bit integer via printf that's compatible between systems. Apparently, 64-bit integers are cutting-edge tech that the industry hasn't been able to come up with a standard for yet. Naturally, getting the game to compile in Linux was more challenging than the server, since I'm using operating system specific things like D3D12 to render and the Win32 API to create windows, read inputs, etc. Also, the threading library I wrote and made a video about directly uses some Win32 API calls. Fortunately, I don't need the game to be playable. I just need to be able to run the simulation and verify correctness of the submitted score. I also don't need multi-threading within the simulation. Multi-threading makes a single simulation run faster by using multiple threads, but trades lower latency for lower throughput. On the server, I want high throughput by running lots of simulations in parallel rather than running a single parallel simulation. Basically, this means that porting to Linux largely consists of my peppering my game code with ifdef win32. There was one change that required me to slightly modify how the game organizes data internally. Previously, I was storing the number of tiles that buildings occupy in the same structure that I was storing D3D resources for drawing the building, and was initializing the sizes and mesh data in the same function. This became awkward when I was if-defing out all of the D3D related code, so I split the data into different structures for things needed to run the simulation versus things needed to render the game. I wanted to be able to print both to a log file and to standard out. To handle this, I made a printlog function that is a drop-in replacement to printf functions. My function is a simple wrapper that passes the arguments to vprintf and vfprintf. A problem I encountered when porting is that Linux var_args is crashy compared to Windows. It seems like in Linux the args are modified when calling vprintf, causing subsequent calls to vfprintf to crash. By reinitializing the args, the crashes disappeared. I also ran into a problem with exit codes. I was returning the verification score as the process exit code. The server would read that code and then either confirm it was the same score as the user claimed, or if I was updating pre-existing scores, I would use the score returned by the verifier. This worked great in Windows, but I was getting weird results in Linux. It turns out that in Linux, there's only a limited set of allowed exit codes, and the OS will modify exit codes outside of that range. I had to make a workaround where I write the value to a file instead, and because I can have multiple processes running at the same time, the server needs to tell the verification what file to write results to. The server will include the thread ID in the file name so that the verification processes don't have a race condition writing to the same file. I also have the verification thread clear the output file before running the verification process, so that in case the process crashes, I don't read stale data. It's an ugly solution, but it works across platforms. As a closing note, I want to mention the Stop Killing Games initiative by Ross Scott. My game isn't a live service game by any means, but I think it's important to consider how a game can continue to work even after I decide not to or can't support hosting the server. The first point is that my game doesn't have user accounts, so there's no login process to worry about. The game does expect a server to exist and will try reconnecting to it if a connection is broken, which can cause lag when it tries to retrieve or submit scores, but this can be disabled in the options. So at the very worst, where I become incapacitated and can't take any further action, the game will remain playable. This video you're watching also provides sufficient documentation of the protocol and internals that a motivated community member could easily make an equivalent server. Upon sunsetting the server, I would also likely release at least the binaries and probably also the source code for at least the server. If releasing the score data and saved games I collect from players is legal, I'd release those also. If you want to try my train game, the Steam page is linked below. If you want to discuss the video, comment below or join my Discord. If you made it all the way through this video, you may enjoy my other videos about programming or want to subscribe to the channel. Bye!